So, good morning and hello everyone. Welcome to another day at the workshop. Today we have a new topic and focus. The idea is that we spend the entire day working with landscape evolution models, that we set up our own landscape evolution models, that we start out with a very simple model. For example, a one-dimensional diffusional fault scarp model. And then if there's interest, I would be very happy to generate a larger scale passive margin model, maybe similar to one of the presentations that we have seen 2 days ago. Okay, so the idea for the next hour is to give you a brief introduction into landscape evolution models. There's no way that I can cover everything about landscape evolution models in the next hour. There is no way that that we can do that. We would need to have a full quarter or semester for this. But we can talk about certain types of models, and we can talk in more detail about the diffusion model that we will be using first. And then we talk about the stream power model. But my understanding is that you already heard about the stream power model a little, right? So I think that's what I saw. Okay, so the title slide here depicts how we can use a real landscape. This is in the Central Andes. We have been doing work on the Puna Plateau, and how we can use gridding ways to understand the landscape. And this is being now done in a numerical sense. Okay, everybody awake? This is no. So? I can use the phone microphone too. This is too complicated. Yeah. Okay. Good. So no, that's not working. Okay. So the idea about landscape evolution models is not new, and has not started with numerical models. It started a long time ago. And it started a long time ago when people started to think about how landscape has changed. And I first talk a little bit about the history of landscape evolution models, just because there is, 2 centuries of landscape evolution models that exist. They may not all be numerical, but they all try to explain how the landscape has evolved in the past millions of years. So people started to wonder how a plateau, an orogenic plateau, Tibetan plateau, Central Andes, the Anatolian plateau, how they have started to change. The concept that has evolved and that has been discussed more intensely in the past 2 decades is, how did the mean elevation change of a plateau? And the idea is you can have a setting where you don't change the mean elevation, where you have a plateau, you start to incise it, and then you start to incise it even more, but you maintain peaks. So the mean, the average of it, still remains the same. Yeah, and then the question is, can a landscape evolution model capture that? And so this is what we often refer to the topography that is rapidly changing. Now we can also change the mean of the elevation by either lowering or uplifting, or changing the entire elevation distribution. And the concept of steady-state topography evolved, where people realized, well, we can change topography, but topography remains the way it has changed. In other words, the topography is very variable, but the topography doesn't change through time. In other words, the mean of the topography over time remains the same. So that concept is something that has been tried to reproduce with landscape evolution models. And the landscape evolution models that first have been looked at, they looked at very different timescales. So we can look at climate as a main forcing factor, and if we integrate over the Holocene, so a more stable climatic period, our temperature did not change much. So let's say the y-axis is temperature. So we can switch between full interglacial and full glacial cycles. The Holocene has been pretty constant. We know that, right? If we go over the last 100,000 years, we had, or 120,000 years, we had one climatic cycle, as you call it. So we switched from full interglacial to full glacial. So we have modified, or we have varied the temperatures by a lot. So we expect a lot of landscape forcing to happen during that period of time. And if we integrate over millions of years, we had several of those cycles. So the question is, to what is landscape evolution responding? Is it responding to this one cycle, or can we have multiple cycles over millions of years, and each of the cycles forces the landscape in a different fashion? And then, of course, there's lag time, interference, and all of these things that come along with climatic forcing. The three classic models, the three classic landscape evolution models from a couple of centuries ago are from Davis, Penck, and Heck. Davis was a geomorphologist / geologist who traveled a lot through Central Asia and has been looking at how mountain belts evolved, and the idea was that he thought about an uplifting mountain belt. Then you had some, this is the relief, by the way, this blue line. So you had an uplifting mountain belt, you started to incise, and eventually the incision led to erosion of the entire peaks as well. So you had a decaying mountain range as well. This is the classic Davis model when you had a constant uplift rate. Penck was a German geologist / geomorphologist who, Walter Penck, who worked for decades in the Andes. He was one of the few who spent years on treks to map and better understand the landscape evolution of the South Central Andes, one of the persons who first defined the Puna Schotter. And he has been in a region that was was not much influenced by climate and did not experience lots of active tectonics, but it was a high orogenic plateau. And he just talked about that when you have a waxing and a waning, you call it, you had a uplift rate that increases and decreases. The idea was that with the increasing uplift rate, you had growing relief, and you maintained that growing relief until the rock uplift rate ceases. So in other words, there is no direct coupling between a rock uplift and incision. So it's an interesting different approach. And then Heck, he is one of the more modern geomorphologists that introduced the term dynamic equilibrium, where for the first time it has been considered that you can have erosion and uplift at the same time and they interact. So that interplay was not clear 150 years ago. So you can have constant rock uplift rate, you grow the relief, and you can maintain that relief for a long time because you have incision, rivers can incise, and you continue to uplift. An idea was that, for example, the Himalaya, where you had high peaks, steep incision, high peak, steep incision, if you look along the Himalayas. So you, or at least the Heck model, argues that you maintain that constant relief because you keep uplifting, but you keep incising, so you maintain that relief. So the reason why I'm showing this is I want you to see that a lot of those models focus on relief. It's the relative elevation change that you're most interested in. Understanding the absolute elevation change is a different topic. It's more about the relative elevation change. Okay, let's see what we have here. Before we dive into some of the examples, so I'm intending to give some examples of landscape evolution models. I just wanted to point out there is some literature available that may be of interest to you. Specifically, we will be using a LandLab later on. There are publications that describe LandLab. You often see the abbreviation LEM for landscape evolution model. There is a landscape evolution model for MATLAB, but this is too simple. We will not be using this. LandLab is a collection of many components that have diffusion, stream power, erosion, landslides, and many other processes modeled in there. That is a very useful environment. This, by the way, the lecture is on the GitHub webpage as well. Okay, so how do models work? And I'm giving some general introduction, and then we dive into some examples. So the two core differences that exist is you can have a gridded model where you essentially have a raster, like the digital elevation model, what we had yesterday, and then you perform some numerical calculation, diffusion, for example, or incision on each of the grid cells. So this is essentially a river that has been depicted in there. I mentioned yesterday also we couldn't get rich DEM to work. My apologies. I mentioned yesterday that rivers, even so the Amazon River may be hundreds of meters wide, it may only be a single grid cell in that model depiction, okay? So this is something to keep in mind, that a river is occupying a single grid cell, even so it may be much wider or much thinner too, right? So if we have a 90-meter DEM and we look at channels in the Himalayas, the rivers are not 90 meters wide at that point, but we use that approximation. Modelers realize this and say, well, we need to have something that is more flexible than a grid. How can we do that? Well, triangulated irregular networks came into play, TINs. And those TINs, they are essentially triangles. Each of those guys here is a triangle, and those triangles adjust to the required spatial resolution, meaning that if you have a flat landscape, you can have large triangles because you don't need much data to represent that surface, whereas when you have steep slopes or when you have a river valley, then you have many, many tiny little TINs that represent that structure in much more details. So TINs is one really nice ways to work with data that has different spatial resolution. By the way, when you work with point clouds, with LiDAR point clouds or something along those lines, TIN is the structure that you most widely use. So because it allows you to have different spatial resolution. So you can do modeling on a grid and on a TIN. For today, we mostly focus on the grids just because it's a little easier and because the stuff that we are doing doesn't rely on TINs. TINs are extremely useful if you want to model river valleys or floodplains, for example, because you have a very different spatial resolution. For the mountain ranges that we work with or that I'm intending to do today, the grid cell approach will be totally fine. I just want you to have heard about this. And the nice thing about LandLab is it can do both. Yeah, so that's the nice thing about LandLab. So what is it usually what we do? We have a couple of input parameters or so-called boundary conditions. So input parameters, for example, can be uplift, rock uplift, can be rainfall. The topography is an input parameter. And boundary conditions are what happens at the site of the model domain. And we will be doing this with a simple fault-scarp model. We can allow mass to leave the model, then we have an open border, or we can say we close the borders and then no mass can leave the system. You know, sometimes you want to have it open because you essentially, when you have a catchment that has a river draining out here, you want to have this side open. You want to have all the mass being able to leave the system. If you keep that side closed, essentially you start piling up sediment at the bottom here. Yeah? So you can change and modify the boundary conditions, and we will set those explicitly. Just a quick note, there is a long history of numerical landscape evolution models. They started with something that is called Siberia, Wilgus, this is Beaumont, then in the early 90s. I'm just pointing out Cascade is a more prominent one. John Brown developed that. Child is a model that is included in LandLab. This is Greg Tucker. Greg Tucker is one of the core developers of LandLab. So he used his several decades of modeling expertise and put it essentially in a Python environment. That's LandLab. Some of the codes are still the original child codes that he's using. So LandLab is not a completely new model. LandLab builds upon some of the existing models and it just nicely combines it in a very, very efficient way. I'm not going through all of these. What is not on there is a newer model called FastScape that Jean Brown, who's now at Potsdam too, developed. And that FastScape is a stream power erosion law, but very, very efficient. So we can run it for millions of years and we can still do it all on our laptops here, and we get a result within 10 seconds or so. So we will be relying on that algorithm. I'm not talking much about algorithms today. I'm talking about the modeling approaches. Okay, I would like to talk about an example of landscape evolution models where landscape evolution models have been used for, and I do this on purpose because I really liked what I saw 2 days ago about the Western Ghats escarpment. That's a really interesting topic, and that's something that many geologists have worked on before. And the general question relates also to the fact, how does a plateau growth, for example. So there are a couple of overarching questions. How do escarpments retreat? I will be showing a modeling study of that. And how do plateau grows? What is a plateau growth region? And you can think about a plateau. Let's use the Himalayas. I mean, we all know where the Himalayas are, right? We have thrust fronts. And you could say that the plateau is growing by essentially a couple of thrust fronts that are pushing out the system more and more. Or you could say that you have the so-called lower crustal flow. This model has been proposed for the Himalaya too, right? That you, at some point, that you have the ability to move more material in a ductile well. Some other people propose that you have intermontane basins that you fill through sedimentation, and thereby you grow the plateau. This is a model that is currently being densely discussed for the Central Andes. So, you know, some people think that this is a way how the Central Andes, the Puna Plateau, has been growing. This is something where people argue this happens in the Himalayas, except that thermochronology data maybe not fully supports this. And it also has been argued that the Himalayas maybe have been growing like this. You know, you have the main frontal thrust, the main central thrust, the main boundary thrust, and so on. And those are all the faults that push it upwards. So these are things you can test with models, especially when you have thermochronology data or some other data that allows you to constrain, structural geology data would work too. Okay, I said that I'm going to talk about passive margins and Escarpment Retreat, and one of the classic examples here is the application of Cascade. That's modeling environment that John Brown developed, and we are looking here at southeastern Africa, and we have an escarpment sitting here, and the question is, how did that escarpment evolve? This is fairly similar to the Western Ghats escarpment. So it's another path of margin. We have those clear steep cliffs. So it's a very old one that is related to the rifting roughly 130 million years ago, and you have a topography or a relief of 1.5 kilometers. And the question is and we discussed this a little 2 days ago, is a plateau, or in that sense the escarpment, is that degrading? So this is the escarpment. Is that degrading by fluvial erosion, where you essentially have diffusion occurring and you end up modifying the drainage divide, so through river erosion, or is a escarpment retreat retreating as steps of a steep cliff that is migrating backwards, right? So those are two different models that we can test. And in a 3D version, this would look like you have an environment where you maintain the steep slope and you are just retreating it. This is something that you call the escarpment retreat, right? Where you have essentially a front, and that front just sets back because you have either high lithology or because you have processes that drive it backward. And this is something that you describe as a plateau degradation, where you have an escarpment, and then you have fluvial erosion that starts to smooth out the surface, so that in the end you essentially have a diffused ramp. Okay, so these are the two models, and this has been applied for Southeast Africa. And the nice thing about those landscape evolution models is that they also predict the thermal field, so you can make predictions of what thermochronological data are supposed to look like. So appetite, fission track, urine, thorium, helium, or something along those lines. So you can predict the distribution of thermochronology data, and these models predict that when you have escarpment retreat, meaning that when you have a wall that is backsetting, you end up getting an age distribution that is, so this is here the escarpment, where you have all the same ages, and then you have, this is a rifting age, right? So ages are set by the time of the rifting because that's the thermal event. And then you start to change the ages, and you essentially see the escarpment retreat that becomes younger and younger in the thermochronology because you are setting it back, and the points closest to the current escarpment are the youngest ones because they have been most recently reset. Whereas when you have a fluvial erosion, essentially a plateau that is eating into the escarpment, you have a much more widely distributed set of thermochronology ages because fluvial erosion is doing the work. Yeah, so you essentially you're eroding top down in the plateau degradation. In the escarpment retreat, you maintain the old ages and you just reset them while the escarpment is retreating. So it's an interesting model, we can flip that around here for the purpose of this model. So if we compare this with this model, right? This is our constant H for the escarpment, or for the unaffected areas of the escarpment, and then the ones that already have been eroded. In the escarpment retreat, you see the increasing ages by time. So somehow that figure doesn't come out properly, but anyway, what this publication argues for, based on the thermochronology data, although very little thermochronology data, is that the escarpment in Southeast Africa has been retreating by fluvial erosion because they don't see a clear temporal signal in the thermochronology data. So that's at least the model for Southeast Africa. That doesn't mean that it's everywhere the case, but that means that for this particular escarpment, that has been suggested. So that was one of the first applications. That's now almost 20 years ago, the publication, though, one of the classic modeling studies. Now, of course, things are much more sophisticated, but that doesn't mean that it's necessarily better. It just means that people spend much more time in modeling landscapes. Okay, so this was just an example of what you can do, and the core thing that I wanted to get across here is that models are great, but you always need some field data to verify it. That may be structural data, that you measure the strike and dip of fault, that may be thermochronology data, that may be erosion rate data, that may be something else that can verify the output of your model. Otherwise you could model pretty much anything you want if you have no constraints for that, right? So, for example, when you run those, I'm going back here, when you run those guys here, you need to have an understanding of the erosion rate. So if you have cosmogenic radionuclide samples from the outlets, you can constrain the erosion rates on your model, for example. Because the difference between this and this is essentially the fluvial erosion rate. If you have high fluvial erosion, your escarpment will be dissected. If you don't have high fluvial erosion, you will maintain that wall that is retreating. So you always need something that you can hook your model in. That's why I've been talking about the marine wave cut platforms yesterday. That's another way that you can, where you have H markers and you need to be able to represent or reproduce those H markers with your model. So these are things where you always need field work. Okay, another quick point that I wanted to make where landscape evolution models have played a big role, and that is in the effect of focused erosion on mountain belts. So this is something, the climate tectonic interactions that has been a big topic in the last decades, where people argue that if you have preferred erosion on one side, you're going to change the shape of mountain belts, right? There is a famous Sean Willett model, this is from the paper, where he postulates, based on a model only, that if you have a side of the origin is facing the monsoon, for example, you are more strongly eroding it, and therefore you are triggering tectonic deformation because you are changing the stresses of the upper crust by having higher erosional flux. So let's walk through this. So he put up a model like this. This is the drainage divide, and the model setup is in a way that you have much higher erosion on one side, lower erosional flux on the other side, and that means that essentially the exhumation pathways are being dragged towards the direction where you have higher surface fluxes. Sounds logical in the first sense, but it also means that if you're eroding more on one side of the origin, that's a brittle process, right? You are in the brittle part of the crust, and how does that affect the ductile part of the crust that is doing the exhumation as well? So, still an ongoing discussions. Nevertheless, that model, I think there must have been generations of PhD students who then either tried to prove that wrong or tried to prove that right? By collecting thermochronological data and doing other modeling studies, or by collecting cosmogenic radionuclide data. So I've been one of those persons too, by the way, at least to some degree. And the idea was that if you have high erosion rates on one side, it may drive the process. One thing that I learned, and that may be not true for every origin, but one thing that I learned is that I do think we may be able to make up for the lack of erosional flux on this side in an ice age, for example, during the glacial stage. So I think when we integrate over longer periods of time, that erosional flux here that now looks low may be much higher because we have glaciers sitting here, for example. And that's at least what we see in the Andes and also partly in the Himalaya. Anyway, the motivate or there has been no, with a few less than a handful exception where field data proves this. There are many modeling studies that suggest that there is a coupling between climate and tectonics, but I have not seen a really convincing field study. A few years ago, we published something in geology, Georgi Grujic and I, and we think that may be an explanation on how the seawallics have formed, but I have not seen a field-based study that would support this fully. So it's a nice modeling exercise, I usually call it. Okay, I talked about this. Okay, let's dive into the details of some of the landscape evolution models. And a landscape evolution model usually has different parts, and you can turn those parts on or off. And the core concept is that you always want to maintain the continuity of mass. Continuity of mass means that whatever you put in, you take out, or the other way around. If you take something away from the top, you need to lower the surface height. So if I go back to that figure, a continuity of mass means that you push in mass here, you take it away at the bottom, and that needs to be, I'm sorry, at the top. That needs to be in balance. At the same time, you may be subducting something, and then the mass disappears. So whatever mass you push in here, it needs to be distributed in a decent way. So that's the core principle. You can't push in mass and then it magically disappears. Okay, that just does not work, and you don't do that. So there is no such thing as the evaporation of rocks or something. Okay, that just does not happen. Many other model components, they, especially when it's coupled to surface processes, they have some runoff component in it. So how do you generate runoff from rainfall, or you use continuous, spatially uniform rainfall, and then you also do the routing of water. That's essentially mostly a D8 routing, what we talked about yesterday, where you do a flow routing of it. And then you have, so by the way, I'm not going into details of the tectonics models today. We mostly focus on Earth surface process models. So mostly stream power, incision, and diffusion models. I'm not going to talk much about large-scale tectonic models that are driven by subduction cycles, for example. We don't go there. So that's why I'm putting here the two domains how you model landscapes. There is no single equation that can do everything. You have to do things in step. And the first part is that you do that you model the hill slopes, and you model the hill slopes by having a transport law for hill slopes. That's mostly is diffusional. I will explain this in a second. And then we have a second transport law for rivers. So this is essentially diffusion, and this is advection. Rivers advect material, and that is a different transport law than the diffusional hill slope transport law that we have. And you can turn those switches on and off. So you can say you generate a model that only has fluvial erosion and no hill slope, and vice versa. And then you can, of course, add to it landslides and other processes. These are then other components of a model. But each of this is essentially a separate equation. There is not a single equation that would have everything combined. Yes? Well, you know, they are They are models that deal with convections in the mantle and shear forces that occur during mantle convection processes that drag the upper plates along, for example. So those are models that are based on the thermal field of the Earth, of the inner of the Earth, and we are not doing this today. That's something that is usually occurring on much longer timescales, and those models are also much more demanding, where we wouldn't be able to do a lot of our stuff on our desktop. So examples are, for example, the hotspot formation. How do you form a hotspot? How do you bring up a drop of magma throughout the mantle? What are the viscosity changes, density changes? So these kind of models we are not talking about today, but they exist and they are great too. But we just don't cover this today. Yeah. Okay, so I pointed out before the continuity of mass, and that usually is being expressed in a way that you say the change of mass over time is equals the uplift minus the sediment flux, meaning that whatever you bring in, you need to bring out too, unless otherwise you have aggradation. So this is just a way of writing the continuity of mass, and then we can say that the sediment flux then is based on certain transport laws. And we can say sediment flux is only based on hill slope transport, or sediment flux is based on river transport and advection as well. So that Q is essentially your sediment flux term, and that sediment flux term may, for example, have gravity-driven processes. That may be landslides, for example, debris flows. That term may also include water-driven processes, so for example rivers, right, or a diffusional process. So you can have several components in your QS that makes that model more and more sophisticated. But that, that's the general framework. So the general framework is you have some uplift, and that uplift doesn't need to be vertically up. It can be also oblique, and then you have some function that describes the surface mass transport, and those are the laws that we are going to look at in a little more detail now. And I will do this in a board in a couple of minutes where we look at the diffusional law. So we specifically will look at QS for a linear diffusion, a hill slope evolution model. Okay. We have this, so if we look at different models or different transport laws, the same setup, the same uplift rate, the same number of pixels here, if we just allow soil creep, diffusion to happen, we develop a landscape that looks fairly smooth. If we allow landslides to happen, we see that the terrain at least is not as smooth as the soil creep. We can also say that we have the landscape doesn't infiltrate, it doesn't allow to infiltrate, all the surface flow occurs, and that essentially generates a very, very smooth surface. Or if we can also use a pore pressure driven landslide model where you first have to set up a certain amount of water in your rocks before you trigger landsliding. So that's essentially a threshold that you need to bring in. So these are examples of running a model with different transport laws, and then you need to decide what is the appropriate transport law for your environment, and that mostly is based on field work. So if you're in the field, for example, for the Himalayas, it would be completely ridiculous to do a soil creep model because we mostly have bedrock. We rarely have any soil there, okay? So that would be but I've seen that. I've seen papers that only do a landscape evolution model for the Himalaya doing soil creep. There is no soil, right? It's all bedrock. There is no soil. You would need to use a landslide model to describe that. So it's really important to have that linkage to the geomorphic process. Whereas if you're in the western United States, in the Midwest, you have those gently rolling hills. Of course you do soil creep. You don't do landsliding there, right? So it's a different setup. There is one, people always, you don't know when a landslide will happen, for example. So the question is, how do we model processes that occur somewhat stochastically? How can we introduce a certain set of randomness to our model? And in many of the models, you have some kind of a random walk process that allows you to make the model less predictive in a way. So in going away from a clear analytical solution, going to something more stochastically, where you may run a model 10 times and the outcome is slightly different every time, but the sum of those outcomes may be closer to the truth than an analytical model. And the approach here that I just briefly want to touch upon, because you will read that word, random walk, many, many times when you work with models, is that the random walk approach. And one way to explain that is it would work really well here on those tiles. If you would have a coin. So a random walk is essentially every time you are at a grid cell and you make a decision where to go next, you flip a coin. So every time the step that you make is completely randomized. And then you end up with an unpredicted pattern. And that unpredicted pattern may be very, very useful to set up initial conditions for your model, because you don't have perfectly smooth surfaces. A surface like this here on the floor doesn't exist in nature. So you always have some random patches. And how do you generate those random patches? You can generate it through a random walk process, for example. So you should just be familiar with the term and roughly understand what a random walk means, because it allows you to generate stochastically more realistic processes. Generally speaking, when you see the topography, and you all know that because you have been in the field, is that when we see topography that is fairly rough, we know that we have maybe gullies, rills, landslides, or something along those lines. So examples are those guys here. And then we see, when we see gently rolling hills, smooth topography, we know this is a soil creep process. There is no other process that would allow us to generate those smoothly rolling hills. Landsliding would generate a very sharp shells. I'm not even talking about glacial models here, because that would add a whole other dimension. But glacial models would, complicate things. We stay away from the glacial realm for now. I'm showing this because this is one of the first models that successfully modeled erosion and deposition, and that is now more than 20 years ago. That it was Greg Tucker when he was doing his PhD with Rudy Slingerland, so you have a starting grid, and for the first time, using the continuity of mass, you could look at erosion and deposition differences. So where do you have erosion and where you have deposition in your landscape? And this is based on a very simple stream power erosion approach. Just wanted to show this, and I think the two last slides, or the couple of last slides that I have, I briefly want to talk about child, and then land lab, and then the diffusion law. I would like to talk about it more in detail. So one of the models that largely dominated part of the community was a child model, the Channel Hill Slope Integrated Landscape Development Model. That's what CHILD stands for. It essentially was the first time the approach to couple diffusional hill slope processes with a channel model. And so, it's a very neat approach. Greg Tucker wrote it, and it made use of tints. I'm not going into detail here. I just want to let you know that Land Lab is mostly built on CHILD. Yeah, so that's a part of the deal. The reason why they moved away from child was that child was written in C++, and the community wasn't ready to program in C++. So that's when Greg Tucker and others, Nicole Gasparini, said, okay, let's turn this into a Python module because there's more interest in using Python and the community is larger than C++. So that was the motivation behind it. And now LandLab has become a big, nice package in the past couple of years. LandLab stands for Landscape Modeling Library, and it essentially combines child, John Brown's models, the Fastscape. It has a landslide. It has vegetation models in it. It has vegetation erosion interaction models, several fluvial models in it. So there are many components that you can add to your model, and I will show you how you do that. For now, we mostly focus on the very simple linear diffusion and stream power erosion rates. And okay. One of the nice things that we can do with LandLab is that we can automatically extract catchments and calculate steepness indices, for example. So we have our modeling realm, we obtain steepness indices, and we can compare that to our digital elevation model, to our real world digital elevation model. Then we can see what are the differences, and we can validate or unvalidate a numerical model. So LandLab has been tailored towards making it very user-friendly for directly extracting the channel profiles, for example, as well. So this is a very useful approach. Okay, I think it's most useful if we dive in and do some of the stuff ourselves. We do it very slow, and I make sure that we all can follow along in Python. My apologies if that was a little too fast yesterday. I did not know what the background is. Maybe I should have been here the first week to see what exactly has been done in the past. Okay, what I would like to do is, I know that you have talked about the diffusional model. I just briefly wanted to write the equations on the board and talk about it, okay? So because we will be using that equation. It's a very simple approach, and I'm going to. I need my hands. Okay. We are going to look at the diffusion equation, and the diffusion equation is usually defined in a way that we are looking at the change of height over time, and this is usually written as dv over dt, which is dv is the height, right? And this is a one-dimensional diffusion equation, and this is related to some kind of a density that may be our bedrock or soil density, and our term that describes the flux. So the sediment flux along the x direction. So we can have some kind of a factor in front of our sediment flux, which is the density of the material. You know, that's like an erosion efficiency parameter. The less dense the material, the more we can erode. And so our change of height depends on what is our flux along the x-axis, right? And we usually have to. Oh yeah, good, thank you. Okay, so the question now is, what do we put in our QS? And our QS, as I said before, can be our sediment transport law, and we are now saying that our QS depends on a diffusional constant, and it depends on the slope. Okay? So I'm saying the sediment transport, this our QS term, now we have our QS term, depends on some coefficient and then on the slope, meaning the steeper the slope, the more transport we have. Makes sense, right? That's usually the approach. So what happens if we put our QS back into our diffusional equation? So if we say we put this guy back in here, well, then we have dz, dt. I should say usually you have the minus here because it means the lowering of vegetation through, the lowering of topography through time. So that's why you usually have a minus here in front. So our change of topography through time, we have again the term of the density, and now we have the term d dx, and now we substitute our QS in, minus k times dz dx. Okay? So all we did is we used the transport law for QS, and the transport law depends on the slope. Very simple. We could have even said that the transport law depends on the slope squared, but let's just say the transport of soil depends on the slope. Okay, so what happens if what is K? K is a constant describing how fast we can erode materials, our diffusional coefficient. And let's assume K is constant along a hill slope. I think for a 100-meter long hill slope, we can safely argue that our K, our soil thickness, may remain constant. If we look at longer hill slopes, it certainly is not constant anymore. But just for the sake of the argument and to make the math a little easier, just say K is constant. If K depends on X, this equation becomes more complicated. We can still do it, but it becomes more complicated. So for K equals constant, we can then say, so this is for K equals constant. So what we then do is we combine our term, this and this, we combine in something that we call D, or sometimes it's also called kappa, the Greek letter kappa. And that's our then final diffusivity coefficient. So we write the equation as the change of elevation in time. And we had a minus here, we have a minus here. If we combine K and 1 over rho, minus K and 1 over rho, that minus on this side disappears, and we have now D. And because we have a D dx, and we have dz dx here, we have d squared z dx squared. So in other words, we are now looking at the curvature. We have the diffusivity coefficient, which has the D is our diffusion coefficient. We call it diffusion coefficient, and that has units of length squared over time. Okay? And then we have our curvature term. Hold on, and we are going to talk about this for a little bit. So first we talk about D. D essentially describes how much material are we pushing down slope. In other words, the units are length squared over time, and we are looking at what is the soil amount or the bedrock amount that we are pushing down slope. Yeah? And so you can think about it, what is the area? L squared is the area. What is the area that we are pushing down? So that is our diffusion coefficient. So if we have very low density, very wet climate, lots of bioturbution, our diffusion coefficient is very high. So we are transporting a lot of material, yeah? If we have dry climate, it may be very low. This is our D. And the second term, now we have the second derivative. Even so, we started out with a transport law that is proportional to slope. Now we have the change proportional to the curvature because we had the ddx twice in there, right? So that's why we have the second derivative, meaning that the transport or the change of the elevation depends on the curvature of the terrain. The more curved the terrain is, the more transport we have, yeah? So that's why people always get so excited about curvature, because that usually describes, you know, if you don't change the slope for a terrain with constant slope, you're not going to change the transport. But if you have terrain where you have changing slope, it means that you have a change in curvature. There you increase or you decrease the transport. Okay, so it's a very simple equation. It's only in 1D, but it can do many, many great things when we want to describe sediment transport across a fault scarp, for example. Okay? K is essentially, K is the soil properties along the slope. So if you envision you have your slope, K is, for example, the thickness of the soil cover. And if we say our K is constant because we have a constant soil cover, you know, we know it's not completely true, but the difference between 1 meter soil cover and 1.1 meter soil cover may not be that big. But if K is a function of X, along, you know, X being along the hill slope, then integrating or differentiating this becomes more complicated, yeah? So this is why most of the time we say our soil thickness remains constant, so we can pull that K out. We can remove that K from the equation, and then we just have 1 over density times K, which then is our diffusion coefficient, essentially length squared over time. Yeah? Okay. The idea now would be, should we, what time is it now? Should we take a short break and then we dive into land lab after? Yeah. Are there questions here so far? Let's put it that way. I mean, you know, numerical modeling people, they're really lazy people. They don't go out and measure soil thickness or soil patchiness. But yes, you should do that. The more information you have about the field, the better it is. And I tell you why, because you know, most of the models that they just say K is constant. But if you talk to a soil scientist, they of course tell you soil is not constant along a hill slope. Soil may be anywhere between 50 centimeters to 3 meter thickness on a hill slope, and that of course you know, is true. But the argument is, well, at long time scales, the thickness remains constant along a hill slope. I don't think that if we want to realistically model the landscape, K is constant. K is not constant. But we just assume it to be constant because it's much easier that way. So ideally, you go out in the field, you can auger and get information about the soil thickness, and you will be surprised how much the soil thickness varies on a hill slope. the examples that we are running, we keep K constant. But when you are generating a more sophisticated model, of course, you can have K as a function of X and Y, K as a function of space. Yes, and we have been doing that in the past too. So if you have, you can make a soil map, a soil thickness map, and you could use that as an input parameter for your numerical approach. Yes. So for example, the models that include vegetation, that look at vegetation-soil interaction, they have a map of vegetation and a map of soil thickness in there. So you have a spatial pattern, and you can use that for the numerical modeling approach as well. But we don't go there today. But yes, you could. I kind of brushed over this, but we can work this out by what is the units of density. What was it? And we have 1 over density, so this will be L3 over mass, right? And we know our diffusivity coefficient is L squared over time. So our K has units of, hold on, that must be, mass over time, right? Mass per length over time, so you're looking at essentially the density of the soil that you are moving downstream, and then you end up. This is mass over length times time. So that essentially means the mass per length per time. So that's goes in the direction of the soil production rate. And this is the term, I don't know if you're familiar with Arjun Heinzat's work. He has been trying to derive the soil production rate. So the question is, how fast can you produce soil? How fast can you convert your bedrock into soil? And that is in that K term, yeah, because you have the temporal, the time component in here. Okay. K is not the soil thickness. K includes the soil thickness, but it's essentially the time it takes to convert the bedrock into soil along the profile. Yeah, so that's it's not a quantity, or the measuring that quantity directly in the field is usually very tricky because you need to measure rates. What is usually being done is you measure the soil thickness, because you assume that when that the soil thickness is related to the soil production rate. So if you have a higher soil thickness, it means that you have a higher soil production rate in steady state. So if you assume there's a steady state condition, then if you measure the soil thickness, then you know how fast your bedrock is being converted into soil, and that is included in here in that rate measurement. But directly measuring K would mean that you, for each sample, you measure the soil production rate, which becomes really, really tedious because you need to do lots of cosmogenic nuclides and so on. Usually you just measure the soil thickness and you relate that to the soil production rate. Other questions? Okay, let's take a short break and then we work our way through land lab.